Can you hear me? Hello?
Yes, sir.
Yes, sir.
Okay, I'm starting. Look at page 73. And anyway, I have forgotten to upload note 8, but I have uploaded later. You should look at note 8. It starts with the introduction of the metric space. And now today, basically, I want to talk about I want to start with accumulation point. This is very important. Okay, this is a special kind of, very special kind of closure point. Look, in page 73, first I'm explaining the idea, motivation. Now look, you start with set A in real line with usual distance. But here you are adding this point. You can see that A bar, that is set of all closure points, will be this and this. Okay, here this is A bar. Now pick up any points here and this thing point 2, compare. Okay, first of all, I can compare with this thing 0. So 0 doesn't belong to A, but 0 is a closure point, whereas 2 itself belongs to A. Remember that A is contained in A bar, so every point of A is a closure point of A. Okay. Now look, in 0, whatever neighborhood you take, minus delta to plus delta, it doesn't matter how small is delta, its intersection A, look, it is not only empty, it contains point other than 0. That means if 0 of course belongs to this and this intersection, okay, its intersection of course non-empty, but in fact if you give this, that is also non-empty. That means, look, here I am 0 omitting, so that 0 cannot be in the intersection. Okay, even then it is non-empty. That means any neighborhood of 0 here contains a point, even though 0 is not here. It will be the same thing because 0 is not here. Contains points other than 0. This is true for any other point in this. Even if you take 0 less than x less than 1, you see that x minus delta to x plus delta interval into neighborhood, this a minus x, this is not empty. That means a neighborhood of x, even for this. For 1 also similar to 0 you have it. If you take any neighborhood which will intersect A in points other than x, okay, that means it will contain a point of A different from x. Whereas look, before that I should tell you that we have two sets, A, B, subset of x, and suppose x is a point. I do not know whether x belongs to this or not, but if I write this, look, this will be the same thing. Sorry, not this one. A intersection B minus x, that means here excluding x will be same as idea is that from the intersection x may belong to this intersection or may not belong to that. But if I write this way, this means intersection A is this means this actually. Okay, that A intersection B, x doesn't belong to the A intersection B. Okay, now thing is that look at 2. Though 2 belongs there, 2 itself belongs to A. But if I take a neighborhood of this, look, this only contains its intersection with A. This interval with A is just 2, not other than 2. So there is a difference that if you have got a neighborhood whose intersection with A is only 2, it doesn't contain point other than 2. Okay.
सर
So,
वन है
सर इसमें
Say again?
एलिमेंट मिल जाएंगे 1/2 1 तक तो एलिमेंट है इसमें।
Sir, 2 minus 2 by 2 is equals to 3 by 2, not 1 by 2, sir.
oh, it is 3 by 2. Okay. Fine. Wait a
So
minute.
3 by 2 to 5 by 2.
Wait. All right now?
यस सर
यस सर।
Yes, sir.
3 by 2, this is okay, fine. So that here is the difference between, though, look, 0, 1, they do not belong to A, but 2 belongs to A. Still, the behavior of 0, 1, you look, that is much better than 2, because you are getting a neighborhood of 2 which does intersects only 2. Whereas, so that's why it is different. But both are accumulation in the closure point. But here is a special closure point. This kind of closure point is called accumulation point. Okay. So that accumulation is a very special kind of closure point. So that you can see that in that I have explained all these things and that. Now I have given the definition. Definition 6. Definition 6. That I told you that. This is in general, if you do that, take XT metric space. A is a subset of X. And X belongs to X. X may not belong to A, may belong to this X. Then X is called an accumulation point. This is a special kind of closure point. It's called an accumulation point of A if, look here, P, X, R, any neighborhood of X with intersection. This I am writing. A minus X not equal to 5 for all r greater than 0. Look, for all greater than 0 means every neighborhood of X. Here I am omitting X. That means it intersects in points other than X. Okay, this is called an accumulation point. Got it? Now, already I explained that what will be the accumulation point, what won't be the accumulation point. Now, definition 7, that A prime, to take the set of all accumulation points of it's called A prime. Like the derivative sign, it is also called derived set. Derived set of A. Now look, previous example, I was doing this in this metric space. So A prime actually is coming this. Okay.
0,1 close.
This is all right or not? A prime?
Yes,
Every
sir.
point inside here is also an accumulation point, right? But 2 is not an accumulation
Yes,
point. So A prime is this. So I have given the result exercise. Okay. Anyway, I have sent a note on that. Whatever I am saying here, that is the tooth problem. Okay. I'm not going to issue any tooth sheet on that. In fact, here you have a lot of problems. I have given page 75 and page 74. That is, you can think of say tooth sheet 2. But whatever problems in between I am telling from Naliprantis Barkinsa, they are part of the tooth problems. Okay. So that here you should do it that A is closed. First of all, A bar, you can see A bar, you'll have to prove that. A union A prime. Look, one side, A prime by definition is this, because it's a special kind of closure point. Sorry, this. Okay. And A is obviously this. So A union A prime will be contained in this. Okay. So that you need to prove this. So basically what you need to prove here that A bar equal to this. Okay. So that look what will be choice. So you start with X belongs to A bar and suppose X doesn't belong to A. Then you'll have to show that implies
X belongs to A
prime.
Dash.
yes sir.
That you'll have to show. That means I can write this way, X bar minus this. Okay. So this result you should prove, and all this exercise make sure that before the minor you should solve all these things. In question 4, other questions are very straightforward. Let me tell you about question 4. That we are doing with this. You can do in general in Rn with this usual distance or even Cn. You can do it. Now I'm saying, look, if you have a set A subset of R, B subset of R, then A plus B, the definition, the addition of the points. Makes sense since R has an addition structure. It makes sense actually in any linear space. Okay, X belongs to A, Y belongs to. Okay, I'm saying that 5, 4. No, it is 5 actually. Sorry, it is 5. 4 is different. Okay, 5. So look here, if you take both closed, it may not imply, it need not imply that A plus B is closed. You should find an example. Okay, right? Think of that. It may not imply A plus B is closed. Okay, that actually I am asked actually, if A and B are both closed in, is A plus B also closed? I am giving you the answer. It is not closed in Yan. So you should give a counter example. Okay. On the other hand, if you
0
just
to infinity A and minus infinity to 0. 0 to infinity A and minus infinity to 0 B.
minus infinity to 0. 0 you'll have to take
Yes,
A
sir.
closed. So this
Yes,
is
sir.
this. And A,
Yes,
this is
sir.
A.
And
What is B?
B 0 to
0 to what?
close 0 to infinity.
So then it is coming the whole R, that is closed.
हेलो सर
A
It
सर
is
m
plus,
प्लस
also
n
open,
अल्फा
sir.
A plus B is what is coming? बताओ.
सर m प्लस n अल्फा वाला ले लीजिए
A plus B will be whole R actually. No,
Yes,
Sir,
sir.
let
But
another
this is
example.
also open.
this doesn't work.
Okay.
Look, you have taken 0.
Sure.
If you take 0, then A will be contained in A plus B and B will be contained in A plus B. So that A union B will be contained in A plus B, but A union B is your R. Got the point? So this is coming close. It is not your counter example.
Sir,
M
take one.
plus n alpha.
I am saying
Hello.
give an example 5A. I'm asking. Actually, I have given the answer that sum of two, this is called sum of two closed set need not be closed. But I'm saying
Sir,
Sir,
take
sum of two closed sets in R need not be closed. This is the thing. If you take this, you just see that. Sorry. Unless you take this, it won't be closed, right? And
Yes, sir.
if you take, you need to take that. Now, since 0 is there, look, then A will be contained in A plus B. Because any element of A, you can write A plus 0. Here 0 belongs to B and A belongs to A. समझ गया? So this belongs to A plus B. Similarly, B is contained in A plus B. So that A union B is contained in A plus B. Of course, A plus B is a subset of R. A union B क्या आ रहा है? R आ रहा है. So R is the closed, the whole thing. So this is not a counter example. Okay, let's
Sir, let
Sir.
another one.
sir,
think
take
about
n A equal
Sir,
to
A equal to
n
what?
union 1. 1 plus 1 by n union 1.
But 0 कहाँ से? Closed होना चाहिए.
hello, sir.
1 by
Union
n,
1 length.
take, which are just take 1 by n. It is not closed.
No, sir. 1 plus 1 by n union 1.
1 plus
1
1
by
by
n.
n. N belongs
And
to n.
union. Yes, sir. And
And
union
1.
union and take b equal to minus 1.
This is A. And B equal to
Minus 1.
A is closed.
So a plus
because
b equal to 1 upon n.
it is going to 1. So this. And what is A plus B?
1 by n.
A plus B will be simply 1 by n. This.
Yes.
How it can be? Think of that.
Sir, 0 भी
Union
आएगा.
0 भी आएगा.
0 भी आएगा.
Check that. Okay. Something is
Sir,
similar to
another.
this you need.
Union 0.
Sir, let another example, sir.
Sorry, sir.
Sir, A equal to Z and B equal to MZ, where M is irrational number.
A equal to Z. Set
B
of
equal to
integers.
MZ. हाँ sir.
MZ.
हाँ sir.
What is M?
B equal to MZ.
Okay, ठीक है. You look at this and then think about an R square. R square, what will you do? Here actually R square it will be easier. You can think of some geometry. Okay. You think of this just first. Suppose you take x axis and you take this thing. Okay, this curve. Sort of parabola. This is suppose here A, this is B. Then what will be A plus B? Look, this is closed. Basically it is two-dimensional. If you take one-dimensional figure, then it should be closed. I am taking one-dimensional. So A, B are closed, and what will be A plus B? Think about it. You can think of this also. That x-axis and this. y equal to 1 by x, where x is greater than 0. You can take even positive real axis. This is your A and this is B. Then what will be their sum? Think about it. Okay. And also think about that. Suppose A is a closed set, but one set is closed as well as bounded. Then can you have it? Closed and bounded. Suppose. Look, examples you are giving me. Hey, this A plus B won't be closed. Huh? What is this A plus B? I think you got
1 by n union 0 आएगा सर सिंगल.
Reason is I was thinking this B is bounded. It's closed as well as bounded. In fact, you can prove if one of them is closed and bounded. Let me write this. In R, suppose A, B closed and B is specially also and bounded. Suppose one of them, then A plus B will be closed. So that for your counter example, you need both of them unbounded. समझ गया? So that your example won't work because you are taking bounded one set. Both you'll have to take unbounded. Okay. So think about it. First you see that whether you can prove this. That if one of them is bounded, then A plus B will be closed. Then A plus B will be closed. Think about it. Okay.
एक अनबाउंडेड सेट सर 2.
Both unbounded will have to. Only then you will get a counter when the A plus B is not closed. That's why
Yes, sir.
I was
Yes, sir,
giving this here. Look here. In your R square I was giving. This is y equal to 1 by x, x greater than 0. One arm of hyperbola. Here you can take positive real axis or put a real axis. That is also unbounded. Both are closed. So this won't be, the sum won't be closed. You can see that geometrically what will be the sum here. Okay. This is A, this is B. You can see what will be the sum here. This won't be like reason is here both of them are unbounded. So that if one of them bounded, then it will be closed. Think about it. Okay. Fine?
Yes.
Okay. Already I proved dense it that xt, if you have a subset of x, then if you have this, not for all set tangent that I told you, then A is called dense. I have given you the example also. Here I have A is called dense in X. Okay, so this is Q, set of rational, set of with rational dense. Now the boundary points. Now look, if you have a metric space Xt, when you're talking about boundary, that means boundary of A. This is this delta, so that del A, the boundary of A. Boundary of A, intuitively what it means? Suppose this is your A, set A. So this is set x minus A, so that it should be the points which are in the boundary of A. That means they should be in the fence of A and x minus A. So this one. Okay. So that's why it is defined. Look, this is defined, definition. A bar intersection x minus A bar. This is the closure of both. Okay. If you have in closure of both, now look, this is the definition, boundary. It has got other names like frontier. Okay. Now look, if you have this definition, you can prove it that interior of A, that I told you that it has to be actually really inside A. Interior of A will be actually equal to, look what will happen. Interior of A. So it should not have any link with x minus A. So it should be x minus x minus a bar. No, not only you are omitting x minus a, you are omitting its closure. Okay, so that I have given the exercise. I think somewhere or I proved it. Interior, yes. Okay, boundary and that. So it should be that really, because x minus a you are taking its closure, and that you are from whole x you are subtracting, then you are getting interior of a. Okay, by definition you look boundary of this, because it should be the boundary of x minus a and a. So that is also same. If you replace a by x minus a, you get x minus a here and you get a here. This is same, which is expected. Okay, fine. Okay. Now the thing is that, and now I'm talking about the convergence of the sequence and that. But why I need to convergence of sequence? Okay. Now look, I have considered three types of points: interior points, closure point, accumulation point, of course you said boundary point. Boundary point means if it belongs to the boundary. Look, boundary point actually depends on this. It belongs to the closure of set and as well as closure of its complement. So that if you can know of closure point, then you can handle this. So basically these 3 points and then. Now the thing is that particularly, but in metric space, the ideas, whether it's called sequential characterization, of this point first. Okay, sequential characterization of closure point. Once you have it, then we have this also. That will tell you that. Okay, but these two are very useful on that. Interior point, it is not that much required, though you can still use on that. Because interior point, I told you that interior of A is x minus so that means you have this closure points there. You just take the complement of that. That will be the interior of it. So that ultimately you need this characterization of closure points. So we'll prefer in metric space, it is possible. But most of the concepts you can handle through sequence. Sequence is not a problem. If you have a metric space X3, that I told you that a sequence in Xn in X is nothing but a function from n to x. Okay, the function that I already told you that fn is denoted by xn. Okay, so that sequence is not, definition of sequence is not a problem. Problem is that how do you define the convergence of a sequence? That means convergence here. Okay, of xn. In x3. Okay, now the thing is that, look, recall that when I introduced metric space xg, I said this is a generalization of the distance in R. Okay, so that when you have a sequence in xn in R and x belongs to R, what do you mean by that? This sequence converges to x if basically any neighborhood of x contains a tail of the sequence. That means if given epsilon greater than 0, given epsilon greater than 0 means any epsilon greater than 0. There exists n epsilon, integer, natural number, belongs to n. This shows that this depends on epsilon such that for all n greater than equal to nxl. Got it? This is the definition. Now look at this definition. What is the where is the special thing I was using? Here only. Other things will follow in any metric space. Okay, na? So here distance was given by this. Here I have d. So that if I replace by this d, it will be what? D x and x, right? So that is precisely the definition of a convergent sequence in a metric space. That I have said definition 10. Okay. Here I have taken instead of epsilon, you have taken r, because usually we take the neighborhoods of x in a metric space is this. Any open ball centered at x with radius r is called a neighborhood of x. That's why I have taken r here. Okay, so that you just take this. That means what will happen? That means here definition, let xt be a metric space xn be a sequence in x and x belongs to x. Then the sequence xn is said to converge to x, if given r greater than 0. That means here I have written instead of epsilon I have taken this. There exists nr. This nr you are writing to indicate this depends on r, because if you change r, it's very likely it will change. Belongs to this is a natural number such that the xn x less than r for all n greater than equal to n. Now look here. It means what? Xn belongs to b xr for all n greater than equal to nr. That means after nr, every member of the sequence will be here. This is called the tail of the sequence. That means, look, basically given r means you are choosing any neighborhood of x. That you should understand. Any r or given r greater than 0 means you are choosing any neighborhood of x, and that will contain a tail of the sequence. The tail of the sequence means after a while everything is there. Okay, a tail of the sequence. That is the means the convergence. Okay, right. And the next thing is that, so this is the definition of a convergence of this. What you got in the real line, you replace that distance, usual distance in the real line by d. That precisely the definition. Now in the real line you have got, if you have a sequence converging to 2 points, then x has to be equal to y. Fine. That means every convergent sequence has a unique limit that I have left as an exercise. Okay. You should be able to prove it. Again, you will be using triangle inequality. Remember that. There you have this kind of triangle inequality. Basically, you are using this thing. X minus xn plus xn minus y. You are doing this. Recall that, what I did. And here you have distance dxy. So by triangle inequality, if you introduce in between xn, this will be it for all. This is the triangle inequality. You use it. Okay, right? Now I have given a small exercise. You should be able to prove it, that if you have a convergent sequence, the metric space, then you take this set A. That means all the members of the sequence. With that, you add x. You add x. Okay. So this will be closed, so that this is closed. Well, here, look, until I have not right now, until now I have not defined boundedness. Okay, so that I think what I'm saying, Cauchy sequence, bounded sequence. First, let me tell you. Okay, I have defined Cauchy sequence, but before that, I think it's better. This is closed. Also, you will see it is bounded. What does it mean by bounded? Okay, right. Now look, in R, when you have bounded, you said, suppose a set A. It's called bounded if there exists M greater than 0 such that you have this. This is the thing. You got it. Okay. But this actually means what? X minus 0. That means you are calculating distance from 0. Okay. Right. Now you can see that. And next I was going to define Cauchy sequence. Before that, I want to define basically bounded set and bounded sequence. Bounded set, bounded sequence in a metric space X3. So I will look at what was I was doing it there. Okay. Now look, I was telling this A is a subset of R. It's called bounded for all X belongs to A. M exists some number. But this means actually you are taking this. So 0 was the reference point. Actually the reference point. But you can also see that instead of 0, if I took any other points, suppose some Y in R, you can see that I will have this for all X belongs to A if and only if there exists M prime greater than 0 such that got it. Here the reference point is 0. Here I am measuring the distance from Y. That you can easily check that why it will happen. It is very simple. One way you look X minus Y, the triangle inequality is this. So this is why we are picking many arbitrary point, but once you picked up it is fixed. So you can take this one as M prime. Okay. Similarly, you can do the other way. So that here, since we have a nice reference point 0 there, we are taking that. If you don't have a point, we could take that. But still you said we are having this point, one reference point. But I could get rid of this reference point of the 0 or Y. How to do that? Look here, so that if I took all these things, now look, I take these numbers. Don't confuse with that Y, where XY belongs to A. Distance between any pair of points in A. We are taking this collection. This is, sorry, it's equal. This is another subset of R. Okay. Look, A is a subset of R. So this is their difference is a real number. In fact, B is a subset of R plus. Okay. Right. You can easily check that A will be bounded if and only B is bounded. A is bounded if and only B is bounded. That means if and only if its supremum is finite. Okay, right. So that look, so that if you take a subset of R, what I'm saying, exercise. A is bounded in R, precisely here, if and only if B, this set. Okay, got it. Why I am doing it? Look here, you are taking the reference point 0, but here I am not taking reference. Here everything I am doing in terms of the points of A. Okay. That means you are taking up the soup of this. Basically, soup of this is finite. Here it is always a non-negative number, so this makes sense finite because it won't be never negative. Okay, if you have something negative number, then you need to say that, like minus infinity, like this. It means it's a real number. Okay, but here anyway it is a non-negative. Okay. So this means this. Okay. Now look, advantage of this, I can immediately translate into any arbitrary matrix. So what will happen? So this I'm replacing dxy. Got it? This is exactly. If this happens, then we say that A is bounded in xt. Now look, this is also called diameter of A. Reason is it has a solid reason. This justification why it is called diameter. Look, when you have a circle and that, if you take diameter, diameter will give you the largest distance between any 2 points on the circle. Understand? This is the largest distance on the circle. If you take the disk, any points which is not in the circle and that will be give you the less distance. You could take this one also. Okay, that will be the largest distance. Diameter gives you the largest distance. So that is why I call the diameter. So that there is a definition. Let xt be xt is a metric space. And I am taking for your convenience a non-empty set. For empty set, you don't need to define diameter. But if you want to define diameter, you should think that whether it will be infinity or not. Okay, anyway, or 0. But I am taking non-empty set. Okay. First of all, you define diameter of A. This is just a notation dA. Some people write delta A, but I do not think that's a good notation. dA is fine. It is soup of dxy xy belongs to A. Okay, this is called the diameter. Okay. First of all, you define diameter. I am defining first thing diameter. Second thing I am defining A is called bounded in xt if diameter is finite. It means diameter is finite. Is called bounded. समझ गया? So bounded set. Okay. But if you take with the reference point that I have given some higher exercise than that. With the reference point also like the real line I have done it, it will be that. Okay, that means what I'm saying, you can prove that. Exercise is bounded if and only if given y belongs to x, this thing, soup of d xy x belongs to A is finite. Here I have taken reference point. From that point y I am calculating the distance of each point of A. Okay. So that means this thing. It will be, so it doesn't matter. Okay. Later on, you will do function analysis third semester, and that their linear space comes every time we actually measure the distance from the zero vector. Okay. So that's a special kind of metric space. If you have such a nice point, it's fine. Still, it will be the same thing. Okay. Now the thing is that what you should prove, that I'm not going to do the proof, that if you have a sequence xn in X, then you just think about this. Okay, diameter of that. So A, first of all, you take this thing. Okay, so diameter of A will be actually this thing, soup of T xn xm nm, because xm and actually xm belongs to n. Okay, or you can write this way simply. This means overall nm. Okay, so that the sequence is called bounded if this is bounded. So xn is called bounded if TA is finite. Okay, so that result is that first thing, every convergent sequence in a metric space Xt is bounded. But a bounded sequence need not be convergent. Okay, like R and with the usual distance is a metric space. There we have seen that a bounded sequence need not be convergent. Okay, right? In fact, look, just see that. But sometimes look at Xt, take that, the discrete metric suppose. Okay, discrete metric. Suppose if I say xn is convergent, what kind of sequence it will be? Xn is convergent in Xt. Okay. बताओ.
Constant, sir, constant.
Point set. Reason is very simple, because look, if xn converges to x, suppose you take, then you take bx half. Okay. It will be eventually constant. It will be eventually constant, because reason is, look, then xn converges to x, and if you take this neighborhood, so there exists n naught, n half actually. N naught belongs to n such that xn belongs to bx half. But bx half is nothing but this point x. So xn belongs to this. That means that is xn equal to x for that means eventually it's constant. You may have in the finite level first few things may be different. That is always possible. Eventually constant. And look, whatever metric space you take, every constant sequence means every element is same. Every eventually constant sequence, let me tell you that. If you take a metric space, any metric space, so any eventually constant sequence, eventually constant sequence xn converges in xt. Okay, but the converse need not be true. But if d is discrete, it is discrete, then any convergent sequence, converse is also true, any convergent sequence is eventually constant. I'm just giving an exercise. You think about it. If you can't do it, it's fine, but it's always good to think about it. Suppose you have it. If you have a metric space with this thing plus this, any convergent sequence, I am giving you a metric space and I am giving you this. Any convergent sequence is eventually constant. Fine. Does it imply question that D is discrete metric? Think about it. The question. Okay. It's not when you think about it, it's not always important to get the final answer. Okay, even if you don't get the final answer, still you think about that what can happen. I am giving you this example. You have a metric space and I am saying any convergent sequence is eventually constant. Okay. First of all, you got every convergent sequence is bounded, but a bounded sequence did not be convergent. Okay. Now the thing is that, so that this is fine. Convergent and bounded sequence you got. Okay. Right. Now look. Suppose you have a sequence. This is the think of that. I do not know whether it is convergent or not. That I don't know. But I have something that after a while, the extents, the members, extents are getting close to each other. Look, I do not hear differences. Look, in a convergent sequence, I know after a while the members are getting close to X. But here I do not have that information on the point. All I know they are getting close to each other. That means what I am saying, given epsilon greater than 0, there exists an epsilon depending on this, such that distance between xn, xm less than epsilon for all nm greater than equal to n epsilon. Look, difference with the convergent sequence. Here I am having between 2 points. I'm saying they are getting close to each other. Okay, right. It is not definition of convergent sequence. Okay. All I'm saying they are getting close to each other. I do not know getting there close to which point. At all it is getting close to some point or not. It may happen that I'm going to explain. If we have this is the called, then xn is called a Cauchy sequence. You can the history in the net you can see about Cauchy, Augustine Cauchy. It's a Cauchy sequence. Okay, next. Cauchy as a person was not a very good person. He was very arrogant. Okay. And he was particularly rude towards younger mathematicians. Okay. So that we will talk about Cauchy all the time. Cauchy sequence will come. Okay. So that it is called a Cauchy sequence. Now look at this. I have given an example. Look, I am thinking about this as a metric space. Q set up. I'm not taking real. I'm taking only rationals. Okay. Now look, I am defining a sequence. This I have taken from Aliprantis, Parkinson. I'm defining. Look, what I'm defining. Take a sequence x1 equal to 1. Then in YAL you are defining by induction xn plus 1 at page 78. Half xn plus 2 xn. Look, this way I can always define a sequence inductively. Because if you have 1, put x1 equal to 1, then you'll get x2. Okay, from x1 you'll get x2. From x2 you'll get x3. And by induction, it is the finite stage you'll be able to complete than that. Suppose xn is defined, then by this formula I get xn plus 1. Now look, you can first look at that. What will be the distance between xn and xn? Okay, right? That's the first thing. It will be very small on that, arbitrarily close to 0, 0. It will go to 0 as nm tends to infinity. This is the thing we write. That is, nm tends to infinity means actually sufficiently large nm. This means you have xn minus x given epsilon, you give me this is for all sufficiently large nm. Now look where it will converge. Look, if it converges, trick is that if it converges, now look, then xn goes to x, xn plus 1 also goes to x, right? The definition of the convergence. So that if you take the limit here, then this will be x. Suppose it converges, x half, this is x, 2 by x. We can solve it. Then you will get x equal to root 2. Okay. That means xn is actually converging to root 2. But root 2 is not here because root 2 is an irrational number. Okay, right? But since they are actually, getting close to, after a while, close to root 2, that means themselves they will be close to each other, right? But the thing is, root 2 is not here. Then you may say, I am playing a trick. I have not taken sufficiently large metric space. Okay. Now the thing is that, first of all, you get the difference. When I have an XG metric space, I do not have information whether it is really large or big or small. Okay, and another funny thing is that I do not know yet that whether it is contained in a bigger metric space. Though here I have it. So this definition, what I'm giving there, xt, after a while they get close to each other. Not necessarily they gather around a point. That makes sense for an arbitrary metric space. For arbitrary metric space, look, you do not have information whether it is big or small. Secondly, whether it is contained in a bigger space where every such Cauchy sequence converges. So that means in general, Cauchy sequence and convergent sequence, they are different. But you can easily see every convergent sequence. क्या हो गया? Every convergent sequence, अरे ये तो बहुत ही झंझट कर रहा है. ये कहाँ से आ गया? कहाँ से आ गया? Every convergent sequence, you can prove that. Every convergent sequence is a Cauchy sequence. That follows from the definition. Look, dxn xm triangle equality. You can write, suppose xn converges to x. Got it? So this goes to 0 as n tends to infinity. This goes to 0 since it converges. Okay. So that this is a Cauchy sequence. So every convergent sequence is a Cauchy sequence, but a Cauchy sequence need not be convergent. A Cauchy sequence need not converge. That's the example in Q. I have given that. Okay, right. So this is the thing, and that you have seen in a counter example. Okay, you can construct many other counter examples also. Okay, right. Here again, you look xt. If if you take discrete metric space, here the Cauchy sequence will have to be eventually constant. That you can prove. So that here a Cauchy sequence will have to be convergent. Okay. So that here every Cauchy sequence converges for a discrete metric. Doesn't matter what is your x. Okay. Now the thing is that it's a situation we are getting that whether a Cauchy sequence may not converge. Suppose you have it, that you have the information every Cauchy sequence converges. Suppose you have it. Suppose every Cauchy sequence in xt, here I am emphasizing, converges to a point in xt. Cauchy sequence, every Cauchy sequence xn you can write to a point x in xt. Suppose then xt is called a complete metric space. Then xt is called a complete metric space. Okay. Now the thing is, this is complete. How to prove it? This is a complete metric space. Well, in order to prove it, let me tell you, if you have this, you can prove it. Suppose xn is a Cauchy sequence. First of all, you can prove that any metric space, Cauchy sequence, it has to be a bounded sequence. It's a bounded sequence. That means it has to be bounded. This is not difficult to prove. Okay, xn has to be bounded. Now the thing is that another thing that is suppose xn is Cauchy and xn has a convergent subsequence xkn. Then this converges. Then xn itself converges. Look here. Actually, intuitive proof is very clear and why it should be easy. Look, if you have Cauchy sequence at the same time convergent subsequence, suppose convergent subsequence converging to x. That means after a while these members they are gathering around x. But xn is a Cauchy sequence. So that means after a while the members are getting close to each other. But already some of those members are there close to x. So that means after a while the members of this sequence itself they will gather around x. So it has to converge there. Basically it is a triangle inequality problem. Okay. So that I have given this. Okay, I think it is 1 o'clock already. I will continue tomorrow. Okay, so that I have given the definition of Cauchy sequence. Make sure page 79, 81 that you read yourself. Then I will continue with this. Okay, this is very important concept, Cauchy sequence, and also tell Bhavna and Dhiraj that problem, the tute sheet. Make sure that it all problems you do it. Okay, you can ask them for special tutorial. Okay, that is page 75. I said, including 74. The first problem is there. Okay, page 75. So then make sure that you do all these problems. So tomorrow I'll take the class because reason is I'm missing 2 lectures for your minor exam. Also in the first week of November, the Diwali week, I may not take any class. Okay, right? So that this Saturday, tomorrow I will take the class. I have already sent you the invitation. Okay. Thank you. Bye.
Around what
Thank you,
time?
sir.
Thank you. You are welcome.
Thank you, sir.
Okay, sir. Thank you.
Thank you, sir. Have a good day.